exact solution says there's no exact solution. There's P over A. And you may be doing it incorrectly, but the results will be acceptable. You might consider that to be anarchism, but it's not. He was a brilliant man. You know, I don't know how many of you had heard of his column analogy, when he was trying to simplify indeterminate analysis. This is it. I love it. I don't use it, but it's beautiful, like a crossword puzzle. Think of a beam fixed at both ends, absolutely fixed. Put a load in the middle. What are the fixed end moments? Well, you can do that. You can use moment area. Oh, better yet, you can use a computer program to find out what they are. But he thought it could be done much more simply than that. He said, well, first, get the simple beam moment diagram for that load. And you know it's PL over 4, where P is the load, L is the length, 4 is 4. It's the same thing. Next, he says, think of the beam as a column. This is sort of a long column. Would you push, please? The column, that imaginary column, has a thickness of 1 over EI. 2 more pushes, please. And the depth of the column section is equal to the beam span. So now the beam has become a column. Then you take that column and you load on it the M over EI diagram, PL over 4 EI. Then you find this total load, which is PL over 4 EI times L over 2. Then you find the compressive stress, which is total load divided by the area. And the fixed end moment becomes simply PL over 8. That's simply. You know, I may not have been able to explain it clearly, but I think you can figure it out. And you know what the main advantage is? Of course, you know it's PL over 8 for a prismatic beam. But if you have a non-prismatic beam, you can use the same method, and it's very simple. Now, when Westergaard, you've heard of Westergaard, right? He was a great mechanician, very serious. Next one, please. And I love this old photograph because, in a way, it says something about the complex relationships between people. Now, Professor Talbot was really the guy who started the structural engineering tradition at the University of Illinois. And it was he who attracted Dr. Westergaard. Dr. Westergaard was brilliant, but he had a tendency to sin. This was during the Prohibition period in the United States. You were not supposed to drink. He drank a lot and he smoked. And, oops. And Professor Talbot is not very happy with this marriage, because in this way he's marrying his daughter. You know, it so happened quite by chance that her sister was a neighbor of mine when she was much older, and she told me all these family struggles that occurred between them. But Professor Westergaard, again, always reminds me of these ancient people who were brilliant. Please continue. When he heard about the column analogy, he said, I can do it simpler than that. I said, all right, let's look at your fixed standard beam. Next one, please. Take that beam and put it in the lake in the woods. Lake in the woods is a little pond near the University of Illinois. Let it float. Next one, please. And then put the simple beam moment diagram on it. And then calculate the pressure. And the pressure at the ends is very easily PL over 8. It's that simple. You can do indeterminate analysis using this hydraulic method. But he was just playing games against it. But now, Professor Westergaard worked in everything. He worked in airport pavements, in concrete slabs, in building slabs, in dams. Everything you can think of, Dr. Westergaard had some sort of a contribution, and he was superb. I would recommend his book on theory of elasticity and plasticity, which he wrote at the end of his life when he was drinking himself away. But it's a great book. It was published in 1930 or something, but it's still worth reading. He said, sort of like what Hardy Cross said, a simple device can yield perhaps 80% of the truth, whereas the next 10% is difficult to obtain, and the last 10% impossible. In a way, he was confirming what Hardy Cross had said, but in a more scientific way. In a way, he was saying, if you're going to be wrong anyway, be wrong the easy way, because you can never, well, I shouldn't say never, because that's a very strong word, but you can never be perfect every time. And yet, he himself was a perfect mathematician and mechanician. A paper of his that I want to bring to your attention is really very impressive. That's all the paper that he wrote. And he essentially said, it's the velocity that is important, stupid. He said this, the next one please, in the year 1933. He said, it's not the PGA, it's not the peak ground acceleration, it's the peak ground velocity. And he figured it out like this. In fact, skip that line. He said a wave velocity could be alpha g, the acceleration, times the period of the wave. And then he thought further. He says, what if as t increases, alpha decreases? Then velocity remains constant over a range of periods. Hey, we know that now, don't we? Huh? And then he continues to say, then the expectation of earthquakes in a given region should be expressed not in terms of the greatest acceleration, but in terms of the greatest velocity. When did the seismologists discover that? I'll tell you when, in the late 80s. And he had said that in 1933. And how? Because he wanted to explain that in simple terms, rather than getting into a whole bunch of hurdy-gurdy. Let me go on to Nathan Newmark. It's very interesting that he did have a Pythagoras in his background. His father had graduated from the Rabbinical Academy in Lithuania at a very young age, was a brilliant man. He migrated to the United States. He married the daughter of a rather well-off family. And then he left the temple and started preaching that the only way to reach God is through sustenance farming. That unless you developed your own food, you would not reach God. And he had quite a following, just like Pythagoras. And because of it, Nate grew up under very poor conditions, because the man kept preaching and never made any money. And they had to live on in fact, Nate told me one day that he tasted his first ice cream when he was 11 years old. And because of it, I forgive the fact that in the 50s and 60s and 70s, he drove a Cadillac, which was poor taste, but he was compensating for his very poor background in some ways. But he too went all over the place. The next slide, please. You know, to me, you know that to make fire, it takes heat, oxygen, and fuel. The next one, please. I think to have Newmark, it took cross Westergaard, and a push to me, and you had the intellectual equivalent of fire. He was a terrific man. He simplified everything. And again, he worked in slabs, he worked in explosions. In fact, he called himself a generalist, which had always surprised me. I can give you all sorts of examples, but I'm running over my time. One that impresses me most is really outside my area of work. But in talking about the slipping of a dam, this complicated case with a very complicated ground motion coming in, he did it like this. He said, well, consider a rigid mass on a flat surface. Its motion is the motion on the ground plus its relative motion with respect to the ground. Next one, please. See, this is where I don't know whether he was smoking something or whether it's chutzpah, just that. He said, let the ground motion be a constant acceleration pulse. I imagine that. The ground motion be a constant pulse that goes over a time t(O). Well, he says, in that case, the velocity of the ground is going to increase steadily and then become flat from there on. Now, if there is a friction force between the mass and the ground, then it'll give it a constant force which can be translated into a constant acceleration. So the ground will go, the mass will go like this and catch up at that point. Next one, please. And so the ground acceleration pulse ends right here. The dam catches up there. Next one, please. Then he took this area and subtracted from it that area. He did that even in the style of Euclid, of Yor. Next. And he came up with the relative slip being v squared, the velocity squared, over 2g into 1 over mu, the friction coefficient, so to speak, minus 1 over alpha. Now look, I admit that in a practical case, mu and alpha are tough, because you don't know where the earthquake is going to come from, and you don't know the friction coefficient. But from this simple derivation, I understand, the student understands, that it has to do with the velocity. And in a way, that's enough. Because the rest of it you don't know anyway. Now, just recently, I came across on the web a discussion of this by a geotechnician at the, is that a university in Dallas? Austin. There's a university there, isn't it? Yeah. By somebody at the UTA. And she was saying, this is a Newmark solution is full of major errors. Not so. Newmark wasn't getting an exact solution. He was trying to teach the observer what is important. The velocity was important. You know the Newmark tripartite diagram. He never said constant. He said nearly constant acceleration, nearly constant velocity, nearly constant displacement. They criticized that, saying that's not exact. It wasn't meant to be exact. It was, as Hardy Cross said, it was a design method. And even if it ain't exact, its results are not likely to be exact. He was a great man. It's very interesting. In the 14th century, there was an école d'Oisme. I don't know whether it was d'Oisme or Oisme, but he was a French genius who also worked like Newmark all over the place in the 14th century before Descartes. And he solved the turtle and the hare, the turtle and the rabbit problem. He said, well, if the rabbit goes at a constant speed and the turtle goes at a constant acceleration, then, next one please, the turtle will catch up with the rabbit when the areas of two triangles are the same. And it's very similar to Newmark's solution for the dam. Brilliance goes on over the years. And to make it simple takes talent. Talent that I don't have, not very many people have. Now, then we come to Emilio, who appears at the end of the string. And unfortunately, it is sort of the end. We're across Westergaard, pass it to Newmark, and Newmark passes it to Emilio at that time. And of course, by the time Emilio goes to Urbana, he already knows everything, in many ways. He has his master's degree here. Please continue. When I was, sorry, thank you. When I was getting ready for the stove, I looked at the archives at Illinois. And I found a letter that Dr. Newmark and Dr. Rosenbluth had written to Mr. Zewart at that time. And I'll give you a very short summary of it. You know, I find it beautiful like a poem, because it isn't everything is this, and we know things exactly. And this was not the design of the Latino Americana Tower, it was an evaluation of it. Next one, please. They say the fundamental period is found to be approximately 2.6 seconds. I ask you, how many engineers calculate a period and say the building is an period of approximately 2.6 seconds? And they give only two figures, two significant figures. I admire that. You may not think it's sophisticated. I think it's very sophisticated. Next, they get the next two periods. They say they're approximately 1.2 and 0.8 seconds. Next one. They say they made estimates of the shears only for the first 3 modes, not for the 92 modes that the building has, but only for the first 3 modes. And we combined them according to what Emilio recommended at that time. And then, now here it becomes a little bit shaky. The earthquake forces we found are comparable to the wind forces, which is W/30 forces they're talking about. Next one, please. But they say the building needs increased stiffness. Now look, would anybody say that today? Increased stiffness? No. Oh, you make them ductile, you make them flexible. But in the year 1951, they said you need to increase the stiffness of the building. And they recommended how it should be done. May I have the next one, please? And they needed improved drift estimates. They were sensitive to drift. I thought it was the end, because Gerardo told me that this was going to be, according to the Aztecos, that you were going to sacrifice me at the end of the talk. And I'm a little bit worried when I hear things like that. And then they say, well, if the structure could be modeled as a shear beam, not with 200 degrees of freedom, but simply as a shear beam. And they do it. They fold everything into a single frame. And they say, we use center-to-center dimensions in order to make it more flexible. And then comes the part. What they knew, what they didn't know. They say that there remains the possibility of the occurrence of an earthquake more intense than those which have occurred in the last 40 to 50 years. So we have to be prepared for that. And now, don't change it. Now, forgive me, don't quote me, because this is gossip. I happened to be with them, with Emilio and Nate, I think it was mid-70s, at a dinner in Boston, Massachusetts. And they were they were debating the maximum ground motion in Mexico. And I think my memory is right. Of course, they'd always estimated things to a single degree of freedom, a single significant figure. But Nate was saying, well, it could be 10%, 20%, and Emilio was saying, I know from probabilistic projections, and I think, Luis, he said 14%, although I could be lying. It may have been 12. 12? Yeah. No, it wasn't 15. So that's what they knew, but they knew what they didn't know. And when the 18% thing came, the Latino Americana Tower did very well. They were dealing with something they didn't know, but they did know what they didn't know. They were, if I could say, they were both wrong. But they were not wrong, because they were expecting something more than what they estimated at that moment. You know, Luis, Emilio was confident that it was not more than 14%. And really, especially in the middle of Mexico City, it's velocity that matters, not the PGA. But they won. And I really think that Lloyd document is in itself worth reading. Now, I may have another 5 minutes. I would like to tell you something else that embarrasses me. In the year 1959, the wise engineers in Southern California gathered together and they said, what is good engineering practice with respect to drift? I'm not exaggerating, this is in a report. I'm getting it directly from a report. They said, well, what do we have to think about? Life safety, non-structural damage, motion sickness. Well, because you do get motion sick if you're in a... Hey, I was, when I came here the day after the 1985 earthquake, and I was on the top floor of the Sheraton, I got motion sickness, let me tell you. Now, and then they continue like this. Well, don't take it away yet. They said, motion sickness? Come on, we're not medicos. Forget it. We have nothing to do with that. Non-structural damage? That's paternalism. Throw that away. Life safety? Well, hell, we're using static forces. We don't really know what the drift is. So make life safety permit twice extra. I mean, permit the earthquake drift to be twice that what they accept for wind. I mean, in the year 1959, never mind that. Up until 1980, we, the gringos, were totally insensitive to drift. That's the truth. You may criticize me. Maybe Nate Newmark knew, but he didn't tell me. Somebody knew. And I'm embarrassed to tell you that. Rosenbluth, in his paper in 1956, and of course, he has to talk about high-level things. He does. But at the end, he says, drift, or story drift, can be obtained from a factor times an intensity. And what does he give the intensity in? He expresses the intensity as a distance over time, velocity. He's sensitive to what Westergaard said earlier in 1933. Then, next Maverick, he says, and this is directly from Emilio's paper, pay greater heed to relative displacements than to stresses. Hey, this is treason, huh? At that time. So don't worry about the forces, worry about drift. And using as the main criterion of design that permissible drift not be exceeded. He knew, he said in 1956 that we should design a building, we should proportion a building for drift, for story drift. How long did it take us to discover that? I should have read that paper. I was around at that time. I missed it. He didn't tell me. I never heard him emphasize it. I can defend myself. It took me till 1979 before I came to the same conclusion. He was simply brilliant. And he is your icon. And you're right. He did establish credibility for Latin Americans in earthquake engineering. But I think part of his greatness came from that string of people that were at the University of Illinois, in Urbana, Illinois, as well as probably your contributions. So I don't want to take your icon away from me. He is your icon. He should be your icon, but he'd also be ours. Thank you very much.
Thank you very much, Matt, for your very, very nice lecture. Now, quisiera preguntas por parte de la audiencia, por favor. ¿Preguntas en alguna parte por ahí?
I talked about gossip. So maybe there are no questions because how can you ask questions about gossip?
Paco Sánchez, por favor.
Thank you very much for your talk. It has been a very enlightening talk and very nice. And I just want to mention that once you mentioned Pythagoras, I think several years ago in this, now that you mentioned, it's just a comment. I want to congratulate you for your wonderful lecture about our icon, Emilio Rosenbluth. And I remember, you make me remember that in this room, someone presented the combination rule as the Pythagorean theorem for earthquake engineering by Emilio Rosenbluth. Because the combination of the sum of the squares is essentially Pythagorean. Maybe with some corrections, but essentially is what you mentioned. It was mentioned in this room several years ago.
So maybe there is something supernatural about me.
Oh!
I knew it happened.
Yeah.
Thank you very much.
¿Alguna otra pregunta? ¿Doctor de la Colina? ¿No? ¿Doctor Stark? ¿Qué pasó con sus discípulos? ¿No preguntan?
Let me get out of here because the Aztecs might be coming.
Well, not having any more questions, that could be a sign that we are very happy with what we heard, and for us it's more than enough.
It's very kind of you.
Very nice. Thank you very much.
Thank you very much for coming.
And, on behalf of the Mexican Society of Earthquake Engineering, and in accordance with your likings of this country and what this country has given us, I would like to present something that we will have to think how we can have a pipe going directly to West Lafayette, but we give you a sample of it, so you take it with you and enjoy it with your wife. Thank you very much. Thank you, Mette, for your kindness. Well, not having finished this lecture, I would like to invite you to participate in the next activity of this session. Don't run away, please. And we follow up, and don't forget that after all this, we will have some brindis and some goodies for everybody. Yeah? Thank you very much.